Hi everyone. Can people hear me? Yep. Okay.
Yep.
Great. All right. How's everyone doing? I guess it's hard to volunteer to answer. I see some thumbs up. Um, does anyone have any questions? So okay, before I let you answer, one thing I saw a question on on Piazza about the Zoom recordings, and I could see them on my screen, or I can see them in my Canvas site, but I checked the student view and I see that they're not there, they're not visible to you guys. The lecture recording from last class. Um, I'm trying to figure out how to do it now. It's not immediately clear to me. I was just doing this over the last 5 minutes or so. Immediately clear how to make the lecture from last time visible. But I'll figure that out soon. I, hopefully, it should take a couple more minutes only of playing around with Canvas. I'm a little new to Canvas, so I'm still trying to figure out how it works. Um, okay, so I'll try to clear that up. Okay, now any questions?
From last lecture's material.
Yeah, or any questions in general. Yeah.
I was curious. I don't remember last lecture how we used the initial velocity condition. Um, I noticed in kind of both solutions, it just didn't really come up. So how is that?
Yeah. Let me pull up the slides from last lecture real quick. So in one, the answer is in one of the in the first solution that we wrote down, we did use it. In the second solution that we wrote down using Fourier series, we did not. We didn't make use of it. Meaning we didn't fully answer the question. So let me just show you. Let me just share my screen real quick. I guess I'm going to share it anyway, but okay. So I have the notes open from last class, and so like you said, we were trying to solve the wave equation, and we were given the initial position of the function, initial configuration of the function, and its initial velocity. And you're asking where is we did saying that we didn't make g involved, right? Is the okay? So when we wrote down the D'Alembert solution, I'm just kind of using this trickery of factorizing um, the wave equation operator, the D'Alembert operator, as it's called now. We did make use of g um, in here you see lowercase g appearing, which is the initial velocity, and then it did appear in our solution as well. So the solution was given by um, taking taking the initial position of the function of the initial position of our wave, translating it in space to the right and to the left at time t, and taking an average of those two, and then taking some type of average of the initial velocity as well. So it did appear here, but you're right. Then and then when we tried to start solving by Fourier series. I mentioned, okay, trying to make the initial data fit, and I brought up the initial position and saying like, oh, okay, the point of this was saying, well, once we try to satisfy the initial conditions, we arrive at this question of can we represent an arbitrary function um, by an infinite series like this infinite series of signs like this. And if I did this, I just did this with the initial position, but I could have done the same type of consideration with the initial velocity. So what I would have done there would, if I wanted to see how to make the initial velocity satisfied, I could take this formula here, my guess for what the solution looks like, differentiate it in time. So take dt of it, and then set x equals 0, and then say, well, that has, so whatever results there. So if I take time derivative here, you just take time derivative of each of these. Pretend you can do it term by term. Take the time derivative of each of these functions. Then set t equals 0. So what will happen is after doing that, sine becomes cosine, and cosine becomes sine. So when we take t equals 0, the coefficient here will vanish, and this one will become 1, and then we'll get kind of the same type of question, but for g, where where instead of the am's appearing down here, it'll be the bm's appearing, or it'll be rather m times bm, that will appear down there. Does that make sense?
So that does make sense. I see where we're using the initial data. I guess I still have a question. Like in the first solution, where we're using the boundary conditions on G.
For the first solution for D'Alembert and D'Alembert's formula.
Yeah.
Okay. So there, you're right that I was also being a little fast and loose. Is I kind of forgot about them, and I wrote down, because when I started trying to write down the solution, the first thing I did was sort of was forget that the function was a periodic, was a function on the interval 0 to pi. By making it odd, I made it a function on the interval minus pi to pi, and then I said, okay, now let's just extend it to a function on the whole real line. So I did, in fact, I actually did something a little bit more general in writing down this formula. As you note that, like, I think just exactly as you've noted, I didn't need those boundary conditions to solve the equation, but the solution that I wrote down still works for those works for solutions that satisfy those boundary conditions. Does that make sense? So I actually just showed you that if you give me any initial data on the whole real line, I can use this formula to solve for it. In particular, I can solve it for data that's periodic, for the more special class of functions which are periodic. Does that make sense?
Yes, it does. Thank you.
Yeah. So I was very quick when I did that. I remember in the last lecture, I just kind of blew through that. But I was kind of just forgetting the periodicity of the function and solving more in general. So yeah, this solution, like, is this D'Alembert solution is a bit more general in that it has nothing to do anymore with periodic functions. Whereas the second type of solution I wrote down, I was selling it to you as being more systematic about finding a solution. But it has the caveat that this only works for periodic functions, or functions on the source. Does that make sense? Cool.
Sorry, let me just clarify. So, if we use the D'Alembert solution, apply it for periodic function, and then we just consider the bits of the solution between 0 and pi, will that be the solution of the? Will that solution satisfy a boundary condition?
Well, I think so, right? Just take a look, right? So f was a periodic function, and so all I have here is just taking these averages of a periodic function. This is still periodic, right? If I add 2 pi, so if I take x, if I look at u, and then I take u of tx plus 2 pi, right? Add 2 pi to x, right? Yeah. Then since f is periodic, nothing changes here in this first line, right?
Okay.
And then down here as well, if I add 2 pi up here, that amounts to shifting as well the integral by 2 pi. And since g was a periodic function to start with as well, then I recover the same value again. So you see the solution is still, periodicity is preserved by this formula.
Fair. Thank you.
Cool. These are great questions, guys. And there was one more question on Piazza too that I just wanted I addressed on Piazza, and you guys also did a great job talking about it amongst yourselves on Piazza. I saw the question about uniqueness. Um, so it turns out that like when we were solving the um, uh, the Cauchy problem, or a Cauchy problem, not necessarily for this particular PDE, but in general for an evolution type PDE. The questions like is the solution unique are often dependent on where you allow the solution that you find to live. Kind of what class of amongst what class of function, right? To make the question mathematically precise, you want to say like unique amongst which functions, right? Um, and it turns out for this problem that the uniqueness part that you get is quite strong. The because of the formula somehow. Um, so this formula kind of ensures uniqueness too, in some sense. But um, in fact, definitely amongst the class of solutions which are twice continuously differentiable. So you got to have to think what do I mean by a solution to this equation? These are kind of PD topics, not so much for analytic topics at the moment, but for PD topic, and when you're asking like what is a solution, you want to ask like, well, what type of function do I want? What do I want to? What do I mean? There's actually different ways of thinking about what a solution is. Classically, this is the wave equation, and you see the equation involves two partial derivatives of u, and so maybe a solution should mean something that has a function. I should restrict to functions that have two continuous partial derivatives, and so that's often what's called a classical solution, that it solves the equation in the classical sense, meaning that everything in this set of equations makes sense once you found the solution, right? I want a function to be twice differentiable if I'm going to say that it satisfies this equation involving two derivatives. And so in that sense, if I just restrict to twice differentiable functions, the solution is unique. As you see from the formula that I wrote down for the solution, well, okay, so it's not clear from the formula, but maybe I want to point out that the way this is supposed to model some physical system, and often in physics, like the notion of energy is somehow important in physics, and it turns out that a class of solutions that one often tries to work with or all functions with finite energy, whatever that means. And we'll discuss this a bit later We'll discuss this a lot more in detail later in the class. We'll come back to the wave equation sort of towards the last third of the class, and we'll discuss all these things: existence, uniqueness, what different types of solutions mean. Once we have a bit more machinery and we can talk about it in a bit more sophisticated way. But anyway, great questions. Okay. Any other questions before I start today's lecture? Okay. So actually, I have a couple more things to say before we start. One, I see some people have signed up for the PSET Partners website. I can't really see what's going on there, but I can. The matching hasn't happened yet, I know, but I can see that people have started signing up, so that's great. If you haven't taken a look, I think the first PSET Partner matching happens on September 4th, which is tomorrow, and then there'll be other matchings after that. But the first PSET is also up on Canvas, so you can take a look. It's due next Friday. By the end of the day on Friday. And the other thing I wanted to mention is that I've started refining this class presentation page, and making it a bit more specific about when these presentations are going to occur. I'd like, if there's a volunteer, please sign up on this Google spreadsheet. So on the Google spreadsheet, there's the left-hand column is the number of problem, and I'll try to, and you can look at the presentation topic PDF to see which number problem you want to sign up for. But they're not necessarily in order. The way that I started them are not necessarily in order of the day that they will appear. So just look carefully at the problems and what day they're gonna, what day of lecture I think they're gonna or office hours I think they're gonna happen. The first one, ideally, if we can get someone to volunteer, the first one I think will happen at the beginning of next class, towards the beginning of next class. There's a lemma from the book that I'd like someone to present, if possible. And then after that, there are two problems from next week's homework that I'd like to open up for people to present in office hours next Thursday. So have a look at this is all on the presentation topics PDF. So have a look there and sign up if you'd like to present next week. Any immediate questions about that? Okay. All right. So at the end of last class, we left off with a question about which functions can be represented by their Fourier series. So today I'm going to try and start making that question more precise. But before that, I'm going to give a half. I'm going to talk about one other partial differential equation, which we'll come back to again later in the class as well, or two others rather. Let's see, is this lecture 2? So Fourier wanted to solve the heat equation, what's called the heat equation, which is the following PDE. So instead of two time derivatives of u, it's one time derivative of u. It's u as a function of t and x equal to 0. But here, x, so t is a real number, t is time. Say positive time, and x is a vector in the plane. And here the symbol, so Laplacian of u, the Laplacian, the symbol means two, or it just means the following. It means take dx squared of u and then add that to dy squared of u. Oh, sorry, u is a function of, maybe I should write this as u of this tx and y. And write xy are numbers, and the pair xy is in R2. So Fourier wanted to solve this equation in the plane, and and at time 0 is given by some initial distribution of heat. So u at time 0 is given by some initial distribution of heat, represented by a function of f of just x and y. All right, so I'm not going to solve the heat equation right now in R2, but rather a steady state version of this. So steady state that you can imagine so imagine trying to like heat a disk of metal, and as time goes on, you think the heat kind of will distribute evenly about the disk, and you'll reach some type of steady state. You can imagine this this component. You're not going to see my finger. The dTu kind of tends to 0, and we could ignore that. So we're just going to solve what's called the Dirichlet problem. Yeah, sorry, was there a question? I thought I may have heard something. So this is called the Dirichlet problem. Please interrupt me if there's a question. So we're going to try and solve the Dirichlet problem in the disk. So given a function f, maybe I'll just give me a second. So we're going to use polar coordinates r theta on R2. So r is equal to, so r squared is equal to x squared plus y squared. X equals r sine theta, y equals r cosine theta. So we're going to change coordinates from the xy plane to the r theta plane. So what this means, if here is x and y, then we recharacterize each point, each vector in the plane as by its length r and by the angle formed with the x-axis. So given, so the Dirichlet problem is as follows. So given a function f of theta on the unit circle, here's a unit circle in the plane, and we're given some function that, so our function is for r equals 1. So the points on the plane with r equals 1 is called the unit circle. So this is the unit circle. We'll call this boundary of D. So it's the boundary of the unit disk. So F, we're going to find a function u of r theta such that Laplacian of u is equal to 0, and u restricted to the boundary of the disk is equal to f of theta. Okay, so this is the PD we're trying to solve. This is called the Dirichlet problem. We'll call this DP. And in polar coordinates, the Laplacian can be written as follows. So D is two derivatives in r, plus 1 over r times dr, plus 1 over r squared d theta squared. So up here I wrote the Laplacian like this. It's dx squared plus dy squared. If I do this change of coordinates to polar coordinates, I can express this in terms of r's and r derivatives and theta derivatives. And this is what the Laplacian looks like. So we're trying to solve r squared dr squared of u. I'm going to multiply through by r squared, so it doesn't look like there's a singularity at r equals 0, plus r dru plus d theta squared u is equal to 0. And trying to solve, so I find u is equal to, this is true. And the technique we'll use to solve this is just, the trick we'll use to solve this is just like last time when trying to solve the wave equation. The second time, we're going to separate variables. So separate variables. Which means we'll write u of r theta is equal to f of r times capital G of theta. So imagine that the solution just consisted of a product like this, where one function just depends on r and the other function just depends on theta. And then if I translate this equation up here to what happens to f and g, I arrive at the following equality. So I need r squared times f double prime of r plus r times f prime of r. this is the Laplacian, the radial Laplacian of f multiplied by r squared divided by f of r is equal to minus g double prime of theta divided by g of theta. So just like last time, I arrive at some equation like this by separating variables. And since the right-hand side doesn't depend on r and the left-hand side depends only on r and not on theta, these two have to be equal to the same constant. Okay, so this is true if and only if there exists lambda in r such that g double prime of theta plus lambda times g of theta is equal to 0, and r squared times f double prime of r plus r times f prime of r minus lambda times f of r equals 0. So I'd like to solve both of these equations. And okay, and further, these are polar coordinates, right? So theta is the polar angles, which is defined only up to multiples of 2 pi, which means I need I need g periodic with period 2 pi. Just remembering that these are polar coordinates. Okay, so this means that I need lambda bigger than or equal to 0, as last time, and as last time, the periodicity means that I actually need lambda is equal to m squared for m and z. So lambda is positive, and in fact needs to be equal to an integer to give periodicity for g. And what this translates to, so this means that, so again, we can argue as before that g of theta has to be equal to some coefficient am times e to the I m theta plus bm times e to the minus I m theta. So all solutions g to this first equation here at the top of the page are expressed as follows. And for now, okay, so now we go back to the equation for f. We try and solve this more complicated looking equation for f. And I'll save you the trouble. So if lambda is equal to m squared in the equation for f, m not equal to 0, then all solutions are given by m, or let me erase this, m not equal to 0. So all solutions are given by, on the one hand, if m is not equal to 0, then f plus m of r is r to the m, and f minus m of r is r to the minus m. If m equals 0, then f1 of r is equal to 1, and f2 of r is equal to log r. So these are all this, meaning all, so linear combinations of these are constitute all of the solutions to the equation for f in the case where lambda is equal to m squared. Okay, but we're looking, this is you can think of this as a physical problem that we're trying to solve, like a steady state heat equation. And which means that we can get rid of the solutions which are unphysical. So as r goes to 0, this solution, this solution has a singularity, right? R to the minus m. This one becomes infinite as r goes to 0. So we are going to toss this one out. And same with log r. As r tends to 0, log r tends to minus infinity. So this one's not, we're not interested in those solutions as well to the f equation. So what we're left with, so we're left with, for each m, have a solution of the form um of r theta is, we'll take the product of f and g in this case, which is r to the absolute m e to the I m theta for m and z. Right, if m were a negative integer, we throw out. Sorry, this top one is misleading. This is m bigger than or equal to 0. If m is less than or equal to 0, we would throw out this solution. If m is less than or equal to 0. So what I mean is, the physically relevant solutions are these, this family of solutions. Okay, and so again, arguing as last time, the linearity of the Laplacian means that we can take linear combinations of these and still get a solution. And of course, we haven't mentioned the boundary conditions at all. That u should be equal to f on the boundary of when r equals 1. So our guess for a solution is we'll take an infinite sum of these with coefficients, summing over all m and z of the um r theta, which is the sum over all m and z of, or sorry, let me call these 8 am times these, am times r to the m absolute m times e to the I m theta. So our guess is that solutions might look like this, like such infinite series, if we can make sense of them, and which we now bring in the initial data. So we need u of 1 theta is equal to f of theta, which is given to us. It's our initial, say, it's our distribution of heat along the boundary of the unit disk, say. And so this is something that's handed to us. And so what happens if we let r tend to 1? So this would be equal to the sum from of am e to the I m theta. So again, we arrive back at this question. And we know from last time that only can hold if the AMs are given by the Fourier coefficients, are given by the Fourier coefficients of f, which are given by 1 over 2 pi, integral from minus pi to pi of f of x. Maybe I'll use theta here. Theta minus I m theta, d theta. Okay, so this is all again motivation for studying a series of this form. And right, so if we are able to represent functions f, periodic functions f, as series like this with these coefficients, then we can solve the Dirichlet problem in the unit disk as well. So this is again we're going back to the question of Fourier series. So let me again rephrase the question from last time. Question Or actually, let me slow down a bit. I'm gonna get to the question, get back to this question, answering this question in a second. And let's set it up. Let's set it up carefully now. So let's frame the question. So let's frame a precise question. Okay, so which functions do we care about? So functions, maybe. Okay, so what? Okay, so let S1 to be equal to all z in the complex plane such that absolute z is 1 equal to the set of all, which identify the set of all x, y, and R2 such that x squared plus y squared equals 1. This is the unit circle. And we'll also use a notation, or maybe more frequently use a notation, T S1 or T1 for S1, which is writing this is the one-dimensional torus. So T is one-dimensional torus. This is just notation. And the objects we're going to consider. So we want to study functions on T or on S1. So I'm going to use those two notations interchangeably, just because I'll probably forget class to class which one I've been sticking with. So study functions on T, and what does this mean? So if Z is an element of T as a subset of the complex plane, then I can write Z is equal to e to the I theta. So again, going back to these polar coordinates, we can identify all the points on the unit circle. Let me draw the unit circle. This is radius. Good. This is a terrible picture. This is T. Where theta is a real number. And is defined up to multiples of 2 pi. So if I think of theta as the polar coordinates, right, that on the unit circle, then we can identify each point on the unit circle with the angle theta formed with the x-axis. But then as we wrap around, we get the same point back again as we add 2 pi or integer multiples of 2 pi to theta. So if we want to express points in the unit circle by z equals e to the I theta, then theta is defined up to adding multiples of 2 pi. So what about functions? So if f is a function on the torus, say a complex or real valued function, so it takes values in C or R, then we may write, so then we can write maybe little f of theta is capital F of the point e to the I theta. So what I'm trying to say here is we can identify the functions. So I can identify functions on the torus, on the unit circle, capital F, these capital F, with functions f on the real line that are 2 pi periodic. So the study of functions on the circle or on the torus, on the one-dimensional torus, is equivalent to studying functions f on the real line that are 2 pi periodic. Okay, so this is the same thing, and you can go further. If capital F is differentiable, then is a differentiable function on the circle, then little f is a differentiable function on the line, and back and vice versa. So this is of course because the exponential function is smooth. So right, if we differentiate little f, we get the derivative of capital F times I, right? Times e to the times I times e to the theta. Okay, so this is just by the chain rule. All right, so this is functions on the circle, or equivalently functions that are 2 pi periodic on R. And okay, what do I want to say? So one class of functions that'll come up a bunch are trigonometric polynomials. F of x is equal to some finite sum e to the I where only many of the an are not equal to 0. So a linear combination of these exponentials of the e to the I and thetas, and is in here and taken over the integers z. And okay, so these are polynomials in e to the I and x. Okay, so this we'll study. This is one particular class of functions, 2 pi periodic functions on the real line. And the main object of study will be what are called Fourier series. So given f, and I'm going to, from now on, just abuse notation. So I'm going to forget about this distinction between capital F here and little f. And I'm just going to, I'm going to forget that a function of the circle is I have to write a capital F of e to the I theta, e to the I theta. And I'm just going to write little f of theta for functions on the torus, just to compress notation, really. So instead of writing f a 2 pi periodic function on R, I'm just going to write f of a function from the torus t to c. So given f from t to c, or equivalently, just going to write it once here, 2 pi periodic. And after this, I'm going to just completely abuse notation by using the same letter for either or. So given such a function, you can associate to f its Fourier series. So given an f, we can associate to it a series where I sum over all n and z f hat of n e to the I n e to the I n x, where f hat of n are called the Fourier coefficients of f. The Fourier coefficients of f. Okay, so this is our basic definition. And we're not saying anything yet about these two things being equal or anything. Just formally, we're given a function f, and to such a function, we're associating this formal object. It's called its Fourier series, without saying anything about other than that yet. So to which, but I guess we can ask, to which functions does it make sense to associate a Fourier series? Right, that can be our first precise question. And well, I guess the immediate answer is those functions which for which the Fourier coefficients are defined, right? Meaning the functions whose Riemann integral. So the Fourier coefficients are given by this integral, right? And e to the INX is a nice smooth function, definitely Riemann integrable, continuous function, in fact. So as long as f is a Riemann integrable function, then you can define the Fourier coefficient. So for the moment, I guess we can say for any Riemann integrable function on the torus, or equivalently 2 pi periodic function on R, we can define its Fourier series. Okay, okay, so let me now get to the question of convergence. So the next object I'll define. So given such an f, or maybe continuation of this definition, the nth partial sum, nth partial Fourier sum, maybe I'll say, denoted by S capital N and F, is given by S and F of X. Is I'm just going to take part of its Fourier series. In particular, I'm going to take the sort of the first capital N, or twice that, I guess. So the sum from elements of the series. So the sum from n equals minus n to capital N of f hat n e to the I n x. So the nth partial Fourier sum is this trigonometric polynomial. You compute the Fourier coefficients of f. You can do this for any Riemann integrable function, right? So these numbers are defined for each Riemann integrable function, and then Sn of x is defined as well, right? Because is now a nice continuous function. In fact, it's a trigonometric polynomial, which are smooth functions, in fact. So this is the partial sum, and of course, the first question that comes to mind after taking an analysis class is, in what sense do these partial sums converge? So remember, when you ask about whether an infinite series converge, the question is really about the sequence of partial sums. So in what sense does the sequence of nth partial sum Fourier sums converge? So the question. So main question. In what sense or for which functions f do we have Sn of x converging to f? Okay, so I've still been vague because if you, as you remember from analysis, there's different notions of convergence of functions, right? We have the notion of pointwise convergence. There's the notion of uniform convergence. So there's various ways we can ask this question, and we're going to kind of ask all of them, or most of them. So pointwise, so first, pointwise convergence. So when do we have Sm f of x tending to f of x for every x in minus pi to pi as n goes to infinity. So if I evaluate each partial sum, if I pick a point x, evaluate it at the partial sum at f of x, in which sense do the sequence of numbers converge to the number f of x? And well, just an observation, it's true if f is a trig polynomial, because then in this case, f of x is equal to its Fourier series. And only finite many are not equal to 0. Right, so in the case of a trig polynomial, only finitely many of the Fourier coefficients are non-zero, and so then once we take capital N large enough, you just have recovered the trig polynomial back again. Okay, so all right, so that's our 0th observation. Next observation. So maybe let me just emphasize that this question, the kind of main thing to focus on this question is, we're going to focus on both aspects of this question. So in what sense and for which functions of f do we have convergence, and then different notions of convergence. Or okay, that means in what sense. The next observation is that, well, the question doesn't really make sense. So the question doesn't really make sense if we study all Riemann integrable functions, whatever that means, right? Or the question of pointwise convergence doesn't really make sense if we're thinking about Riemann integral. Like the question, do all Riemann integral functions have their sequence of partial Fourier sums converging back to that function? It is obviously false. I claim it's obviously false. Well, once I tell you the answer, it's going to be obviously false. I don't think it's super obvious before I say why. So I should maybe phrase it like that. But does anyone can anyone think of why this might be too broad of a class of functions to consider? Why can we not expect pointwise convergence back to of the Fourier sums back to the function if we just consider all Riemann integrable functions?
Is it just that you can change one particular value of a Riemann integral function and nothing else changes?
That's exactly right, right? These two functions, so if I just draw this function, say here, and then this other function where instead of this value here, I assign it this value here, the integral doesn't change, right? So in particular, none of the Fourier coefficients for this function would change. And so either the partial sums are going to converge back to this function or to this function, but they can't converge to both, right? Right. So the question just doesn't really make sense if we're just allowing all Riemann integrable functions. So we're going to need to start refining the group of functions that we consider to ask this question of pointwise convergence. So let's reformulate the question a bit. So reformulation.
Just real quick on that example, could you explain why the Fourier coefficients don't change? Because you certainly could imagine a sequence of functions that converges to the one on the right.
Exactly, right. Or the one on the left too, right?
Right.
Um, so, but let's remember what the Fourier coefficients are given by. So the Fourier coefficients, if this is, let's call this function f1 and this function f2. So the Fourier coefficients for f1 are given by the integral. I guess the short answer to the question is specific about the question of Fourier series. It's Fourier series converging. And I claim that these two functions have the same Fourier series. So this e to the minus I in x, f of x dx. And I claim this is also equal to f hat 2 of n, right? Because all I'm doing in this integral is multiplying by e to the I in x. And so the integral doesn't, right, if you think about how I would compute the Riemann integral of f2, well, I compute it up to right here. I just ignore this one point, which integrates to 0, kind of, right? Remember, a single point, and integrate here as well. So these two integrals are the same. So all the Fourier coefficients are the same, right? So the sequence of partial sums associated to these, sequence of partial Fourier sums associated to these two functions are exactly the same. And so the sequence of partial sums, if it converges to a function, it can't, it converges to either this one or this one, but it can't converge to both, right?
Right.
So this just means that this is a bad question, right? Because doing something like this is a silly, this is kind of a silly example that we want to just dismiss of. So really, when we're considering this question of pointwise convergence, we want to get rid of examples like that. And, a natural thing to do is say, well, what about if I just restrict to continuous functions? So this is Fourier's false conjecture. And it's we're going to prove that the conjecture is false in class, but this is what Fourier thought. Fourier thought, well, this is kind of the only, like points of discontinuity are really the main enemy here. And I think he conjectured really boldly that he said, so if f is continuous and periodic, our notation for this will be f is an element of C0 of t. So the continuous function, so this C means C for continuous, and I'll explain the 0 a little bit later. Then Sn of f of x converges to f of x as n goes to infinity. So if the function, he said if the function is continuous, so for every x and t. Fourier conjectured that if a function is continuous, then its Fourier series converged back to the function. The sequence, meaning in a pointwise sense. So the sequence of partial sums converge pointwise back to f. And let me emphasize that this is false, but it took a very long time to resolve. And in fact, so outside this scope of this class, so a theorem, this is deep. The proof is difficult. And this is by Lennart Carlson. In 1966. So it wasn't resolved until 1966 when Carlson proved, I'm sorry about that. I just had my COVID test, so I know it's not COVID. just talking a lot into the microphone. So Carlson proved if f is square integrable, so he relaxed the condition of okay. So let me phrase this slightly differently. So Fourier's conjecture is false. We're going to write down an example of a continuous function where this conjecture fails. However, it doesn't. He was kind of close to being right, or remarkably close to being correct. And the theorem that I'm writing down now is the precise statement, the precise true statement that where what Fourier conjectured isn't quite true. However, if f is square integrable, for now you can just think of it as a square Riemann integrable. In fact, it's even more general than this. So if f is square integrable, then Sn f of x does converge to f of x for he corrected Fourier's conjecture as follows by saying almost all x in t. Okay, so this is cheap because I didn't. So what Carlson proved was that for almost any, if you give me a function that just is a Riemann integrable function on the torus, and you give me a random point on the torus, if you close your eyes and pick a random point from the torus, then the Fourier series, the sequence of partial sums does converge at that point. So basically what he was saying is that as long as if I write down the Fourier coefficients for these two examples, as I wrote down here, well, and if I just look away from this bad point, then the Fourier series what happens is the Fourier series comes back to this, converges to this function, and these two functions only differ at one point. So what Carlson proved was that this is the only way in which this fails, where it fails at this conjecture holds in fact for in particular for continuous functions for almost every x. Okay, so this is a super hard theorem, and Carlson won the Fields Medal for proving this in the middle of the last century. And we won't cover this particular result in class. We're going to get as close to it as we can, though. But okay, the place to we're going to try and get as close to this as we can, and the place to start really is to let's start trying for ourselves to make sure that these that the questions we're asking make sense. Okay, so a reality check or sanity check, or I'm not sure what the right. So sanity check. Let's try to first establish the question of uniqueness. So, so the theorem. Okay, so what do I want to say? So if we had S and F tending pointwise to F, in a reasonable, so again, forgive me for being a little vague here, in reasonable sense. So if we had some type of convergence, if we can recover F from its Fourier series by taking a limit of the partial sums, then what we're really saying is that the Fourier coefficients would determine F, right? Because we could just take a limit of the partial sums, which are formed by these trig polynomials with the coefficients being the Fourier coefficients of the function. So if we had this convergence, then the sequence of the Fourier coefficients gives us all the information we need about the function. So in fact, they determine f. So what we'd like to know is that if two functions have the same Fourier coefficients, then the functions have to be the same. This is the question of uniqueness. Have we formulated things in a way where we can make sense of these questions, right? So the claim. So we want to know if we have two functions, if we have f and g, and f hat of n is equal to g hat of n for every n, if they have the same Fourier coefficients, do we have do we have f equals g? And of course, you may object that a few seconds ago I showed you an example where this fails. Right, for these two functions, they have the same Fourier coefficients, but are different functions. So the theorem, we show some additional information about f, and what let's do for a second is let's pretend that let's pretend Fourier gave us his conjecture and we're trying to prove it. So let's start by like restricting to the class of continuous functions on the torus, and start asking questions about these. So the theorem is that if f is continuous on the torus, so this is if f is continuous, then if f is continuous on the torus, and if f hat of n is equal to 0 for every n, then f is the zero function. And note that this settles uniqueness, right? So, sorry, Mark. Since if f hat of n is equal to g hat, if I had two functions where f hat is equal to g hat, then if I do the function integrating, finding the Fourier coefficients is linear. So then I'd have f minus g hat of n is equal to 0 for every n. So if I take the difference of the two functions, right, their Fourier coefficients would all be 0. And so if I can prove then that the resulting function has to be 0, then that means that f minus g is equal to 0. Okay, so let's start the proof of this uniqueness theorem.
I just had like a quick comment or question before this.
Yeah.
I guess this just seems really surprising to me because so these Fourier coefficients are like a countable number of real numbers, and it's surprising to me that it determines an entire function on like an entire interval.
Sorry, I'm trying to find out who's talking. Michael, right?
Yeah.
Yeah. I think that should be surprising.
Okay.
Yeah. Right. This is. I think this is one of the reasons why. Right. So what you're saying is like any version of this question seems surprising to you, right?
Right.
Yeah, and I think that's like I think you're kind of in good company. This is exactly, as I said last time, what Euler thought. So Euler and Bernoulli also thought this question was ridiculous, and I think it should be surprising. So we're gonna like. So meaning I think it should be surprising at first glance, and hopefully we're going to develop enough machinery that at the end it's no longer surprising. Is that
Yeah.
that's a cheap answer, but maybe a better answer is like I kind of agree that this is sort of amazing that this works.
Okay.
Um, so right, because even so, okay, so what else? Maybe a couple caveats, like it's not going to work for continuous functions, but it is going to work for functions which are just differentiable. I mean, even weaker than that. So functions that are C1 functions that have one continuous derivative, the Fourier series of that function are going to converge to that function uniformly, in fact.
Can I say something to Michael's
Yeah,
point?
of course, yeah.
I read this thing a while ago that says that a continuous function only needs to be defined on the rational numbers anyway, because then the value at irrational numbers.
Oh, that's a good point, right? Because that's dense.
Defined. Yeah, because it's dense, and so then so a continuous function only needs a countable number of real numbers anyway.
Sure. Yeah. Okay. So that's a good that's a nice way to think of it. Too. Uh, yeah.
Is that still true for square integrable functions?
Um, okay. So Riemann integrable functions, yes. But we're going to, part of the class is we're going to realize some of the deficiencies of the class of Riemann integral functions, and we're going to allow for a broader class of functions that we're going to redefine it. We're going to redo integration sort of, and when we use the word square integrable functions later in the class, it will be a larger class of functions for which this isn't which can be quite crazy, in fact. So Riemann integral functions aren't so crazy. But okay, so for now, let's just like think about continue. Like So I'm gonna push back a little bit at this last point, and I still think that this is surprising. And here's a reason. So if you're into your analysis classes, you might have considered like functions that emit a power series representation. So expanding a function in terms of a power series, and it turns out that is the functions which you can do that for, which emit a power series representation, that is extremely restrictive, right? Those are called analytic functions, and it turns out that that sort of knowing if you have an analytic function, you only need to know the function and its derivatives at a single point to kind of determine the entire rest of the function, what the entire rest of the function looks like. And so here the claim is that the functions that we're allowing can be actually quite bad, right? Let's imagine that Fourier's theorem is true. It's almost true. The continuous functions can be quite crazy, and it's kind of surprising that I think that they can be represented by their Fourier series. I guess how surprised we are is a really subjective thing, but it's not totally convincing to me that this should be. Well, okay, we haven't really phrased the question yet, but I'm a little bit with Michael's first reaction that I'm surprised this works at all, a little bit, even how given that I've read the book before. Okay. All right. Let me see. So are we gonna have time to prove this? Maybe I'm going to postpone the proof of this theorem till next time, because I think it's going to take more than 5 minutes. And I'm going to instead state and prove a corollary of the main theorem, which tells us which is going to give us our first answer, the first real answer to our question. So okay, so on the one hand, so let's assume for a minute that we have this theorem that knowing the Fourier coefficients of a continuous function completely determines the function. A corollary is the following. So suppose f is C0 function, a continuous function on the torus, and suppose I know something about its Fourier coefficients. That if I take absolute values of them and then sum, the series converges. Then Sn of f converges to the function f uniformly on T. So not only do the sequence of partial sums converge, we in fact have uniform convergence on the circle. So what this is saying is that if we have some information about the Fourier coefficients, if we know this is sort of a nicely behaved series and that it converges absolutely, the series converges absolutely, then you have uniform convergence of the Fourier series. All right, so one of the things we're going to work hard on is to try to determine which functions satisfy this criteria. Right, since it's not immediately clear that any functions do. Okay, and the proof is as follows. So I want to give this proof today because this is going to prompt of some real analysis techniques that I'd like you guys to look at over the weekend or before next class to remind yourselves of. So one, by Weierstrass's test for uniform convergence, this sum being finite implies that this convergence is uniform. Okay, sorry, I'm jumping the gun. This converges, maybe I'll write like this. This sequence of partial sums converges uniformly. Uniformly to some function g on the torus. So we can make sense of this limit, right? So I can define this function g minus infinity of f hat of n e to the I n theta. Okay. The second part of the proof is recall the uniform limit of a sequence of continuous functions is continuous. So since each of the S and Fs are continuous, the partial sums are all continuous functions. They're trig polynomials, and they converge uniformly. The limit of is also continuous. Recall uniform limit of sequence of continuous functions is also continuous, which means that g is a continuous function on the torus as well. Right? So these are the two real analysis facts that I want you to take your time to look back up. One is Weierstrass's test for uniform convergence, which I'm just saying here. This is true. So look this up. And one that the uniform limit of a sequence of continuous functions is also continuous. It's a second fact to look back up. And one place is the analysis book that I posted on the Canvas site. And next, note that the Fourier coefficients of G are the same as the Fourier coefficients for F, right? Just by, I can integrate, since I have uniform convergence, I can integrate term by term, and I can show that the Fourier coefficients of G are just given by F hat of n. So this implies that F hat of n is equal to g hat of n by term integration. And this implies that f equals g by the previous theorem. So this is why I say this is a corollary of the previous theorem. So once I know that the Fourier coefficients are the same and the two functions are continuous, then I know that the functions are the same as well. Okay, so we'll stop here. I'm sorry that this last bit was a little rushed. And next time we're going to prove the uniqueness theorem at the beginning of next class. And then after the uniqueness theorem at the beginning of the next class, if you look at the class presentation site, there's room for presentation if there are any volunteers for that. So either, so use a sign up sheet, and once someone signs up, I can get in contact with them about the first presentation, class presentation. Okay, any questions at the end of class? We're out of time. I have time. I can stick around for questions if people have them. Oh, and one other thing is I have office hours immediately after this. So my first office hours are today at 4. I'm going to open a separate Zoom for those office hours if you'd like to continue asking questions in. So if any brief questions I can answer now. If not, I can see you in office hours.
Is Carlson's result known to hold for like other groups?
Oh, boy. I'm not sure I know the full literature on that to answer. Sorry about that.
Thank you.
Yeah, thanks.
Thanks.
Professor,
Yeah.
will
Go
there
ahead,
be
go ahead.
okay? Will there be like a review of real analysis convergence facts, or is that something we should do on our own?
This is something that I want you. I'm gonna prompt some of that with the first homework.
Okay.
So if you look at the first homework assignment, there's a bit of review embedded there, and in fact, I'm going to ask you to try and reprove for yourselves this last result in that first homework.
Okay.
So we'll try to do it sort of as we go with the homework, but I won't do any like set aside time during lecture for a review. I mean, we're always happy to talk about it in office hours. Yeah.
Okay. Cool. Thank you.
Thanks.
Is there a way we can find the Zoom room for office hours?
Is it? Do you guys see it? Do you see it in Canvas?
Let me see.
So let me look at. I'll try and look too from student point of view. It's hopefully in Canvas.
Oh, I got it.
You see there,
Yeah.
I just posted it earlier today, so it wasn't there earlier. So you see it now, Christina?
Yeah, I do. Thank you.
Okay, great. All right.
Just one quick question about the result by Leonov. When you talk about the square integrable function, is it integrable but not in the Riemann sense, but
In the Lebesgue sense.
so-called?
In the Lebesgue sense, yeah.
Okay.
Yeah. So the Lebesgue integrable functions, then the Fourier series converge pointwise almost everywhere is the formal result of Carlson.
Okay. Thank you.
All right, I'm gonna exit now, guys, and then I'll be in my office hours.